So the directional derivative of a function f at location a and in the direction of u, or moving in a direction parallel to the unit vector u, is denoted by the u directional derivative of f evaluated at a. And this symbol means we take the limit as t goes to 0 of f of, and then we look at the location a and move slightly in the u direction. Compare that to the value of a where we started and divide by t. So we're doing a usual limit quotient definition of a derivative. Let's grab a picture to see what this looks like. Okay, so here's some function f. That's the graph of f, that orange sheet there. And then I've chosen some location a, and we're going to be looking at how the value of f changes at this location. And then I've also chosen a unit vector u. So we're going to look at how the value of f changes as we move this direction parallel to u. And so you can see it looks like it's going to be increasing. Now, to make that precise, a handy idea is to say, let's parameterize this path that passes through a in the direction that we want. And luckily we know how to do that. If we take c to be a plus tu, then we're going to have the parameterization of this line passing through that point exactly when we want, by which I mean that c of 0 is just a. So that means that we're looking at the limit as t goes to 0 of f of c of t minus f of c of 0 with respect to t. And if you squint your eyes at that for a second, you realize that this is the time derivative of f of c of t evaluated when t is equal to 0. And that'll be a handy way to think about it when we try to understand directional derivatives in terms of partial derivatives in the next section. But for now, let's just take a look at what f is doing when we constrain to this path c. Okay, so here I've taken the same graph and now I've sliced it with the plane, the vertical plane that runs through this path that we've chosen. And you can see how f is changing as we move over this parameterized line that we have going through the xy plane. Let me draw a slightly better picture for you. Okay, so here's what it looks like if I remove the plane and just show you the path itself. So here's c of t coming through the base. And then if I look at this curve running over the surface here, this one is the one that has xy coordinates given by c of t, and then a vertical coordinate given by f of c of t. And so if we are at the location a, then this height up here, this is f of a, and as t increases from 0 at this point, we're looking at moving in this direction, and so that means that we're coming up this curve like so, and the directional derivative of f at this point is giving us exactly the slope of this green line. And so if you're at that point, moving in that direction, the directional derivative tells you how fast f is changing there and in that direction. Notice that if we were to take some other direction at this location, like maybe I took this direction here, then we'd be moving this way from the point, well, this way, from that point, and looking at the trace above that on the surface, we see that it looks like actually the height of f remains more or less constant as we move in that direction. And so the directional derivative at a in this new direction, maybe we'll call it v, might actually be 0, as opposed to the one that we looked at before where it looked like it was definitely positive.